My name is Kyusang Cho, and we're excited to present our work, Tilt and Average, Geometric Adjustment of the Last Layer for Recalibration. So this was done with my professor Chan Hyun Yoon, and my name is Kyusang Cho from KAIST, and will be presented at ICML2024. In real-world decision-making systems, the model should not only make accurate decisions, but also indicate how certain they are when making the decision. For instance, we may infer from the fact that A has higher confidence than B, that prediction made on A is more likely to be accurate than B. So the confidence can be seen as the level of certainty the model has about its predictions. When it comes to neural networks, because the neural nets are black box models, confidence estimate of the network is a significant signal assessing the model's prediction. Confidence is calculated as the maximum softmax probability from the last linear layer. So from previous works, it is known that neural networks tend to produce overconfident predictions, that the confidence of the predictions tend to be higher than the accuracy. For the predictions to be reliable and trustworthy, model calibration is studied to reflect reliable confidence estimates to quantify the uncertainty of the prediction. So recalibration, also known as post-hoc calibration, targets the problem with additional dataset. In this scenario, we aim to tune the model, which was already trained with the additional dataset. So when we look at the feed-forward scheme of a neural network with the feature extractor and the last linear layer, previous approaches for targeting the problem of recalibration are to design calibration maps. The calibration map is a parametric or non-parametric functions that map the class-wise softmax probability to the calibrated probability. The research points were to design an appropriate approximator for the calibration map that does not introduce degradation in the accuracy with better calibration performance. For example, widely used temperature scaling scales the class-wise score with the scalar T temperature. The main idea of our paper comes from a closer look into the last linear layer. Let's denote the input of the last linear layer as penultimate feature vector. The class-wise score can be seen as an inner product between the row vector of a weight matrix, which we will term it class vector, and the penultimate feature vector with a bias term. This equation can be further split into two aspects, the magnitude terms and angle term. When you manipulate the class vectors, we may control the class-wise score term and therefore can result in a better calibration performance. We focus on tuning the angular aspect from the high-dimensional geometry in this work, with discussion on the magnitude terms in the paper. So the figure explains our method, tilt and average. To manipulate the angular aspects, we propose tilting the class vectors. After that, we apply weight averaging to compensate the accuracy. How do we manipulate angles? We apply tilt, and tilt is based on the rotation transformation in high-dimensional space. So how do we tilt the class vectors in high-dimensional space? Inspired by Euler's rotation theorem in three-dimensional space, we apply a compound of elementary rotation to generate random rotation. So how do we control the intensity of tilt? We define mean rotation over classes, MRC, as the mean angle rotated by a rotation matrix R. The plots below demonstrates the effect of tilt, As the number of rotation increases, MRC reaches 90 degrees in the plot lower left, and the distribution of shifting of the angular aspect is clear when the MRC is 30 and 45 degrees. This effect is proven by Theorem 3.2 and Proposition 3.3 in our paper, so please check our paper for the complete proof. Confidence is relaxed, but the accuracy may collapse when MRC increases. This is natural because we may understand tilting class vectors from the last linear layer as injecting noise. This becomes severe when the MRC increases. We come up with the next step of the algorithm, average, because of the collapse in accuracy. Average is vector averaging unequally tilted weights, which is similar to ensembling approaches. The insight here is that geometric mean is applied on softmax members when ignoring the bias. As you can see in the plots, accuracy is compensated as number of ensembles increases. So this is the full sketch of the overall method again. Since our approach is orthogonal to the previous calibration map-based approaches, we test our method by applying our method sparsely and completely. We may observe when our method is applied, we may yield better calibration performance. So one discussion here is that temperature scaling or other methods based on temperature scaling of adjusting the T can be interpreted as tuning the magnitude. So one contribution is that, to our knowledge, our paper is the first to provide the method to tune the angle. Also, data efficiency is another important thing because we need additional data set to apply calibration. And by experiments, TNA is as data efficient as temperature scaling, since the method optimizes a single parameter theta, which is MRC, similar to that of temperature scaling itself, in which we also optimize a single parameter T temperature. Thank you, and please check our paper for the details from the QR code.